Right, welcome back. Electronic packaging and manufacturing, and we will continue and wrap up our discussion on reliability today. So, today is electronic packaging reliability, lecture number 4. The concepts that we are going to cover today is the physics of failure, failure modes again, some of those. We will see some, we will get introduced to some new or some modes of failure, and POF models, which is physics of failure models. Okay. Not necessarily in this order, I mean we are going to probably jump from one topic to other just to maintain the flow of the lecture, but these are the basic concepts that we will cover today. All right. So, what is physics of failure? See, in the last lecture we talked about accelerated degradation testing and modeling. So, that involved taking a lot of data on the field or under accelerated degradation conditions in the lab, and then using some statistical modeling tools to extrapolate the degradation under normal operating conditions. All right. Physics of failure, on the other hand, is more about trying to understand what is happening, what is the root cause that is responsible for a certain particular failure or mode of failure. Okay. So, it is a methodology that is based on understanding the root cause of failure, and with the knowledge of materials, hardware configuration and the history of life cycle stresses. So, for all this, it is not just going and collecting a lot of data, it is about understanding that what can happen under these conditions, under these operating conditions, with this set of materials that I am talking about, and with this history of this product or component. Okay. I can buy a second hand computer, or I can be selling a refurbished computer, right. So, I need to know that during the previous during its tenure under the previous owner, what kind of operations and stresses did it go through, right. So, these days a lot of we hear a lot of data analytics using data science, deep learning, taking a lot of data using sensors and trying to result in something or model something which is called a digital twin, right. So, a lot of it depends on what is, if you for example, you take two cars and I drive one, same model from the same factory, same lot, I drive one and my friend drives another. Our driving patterns, techniques, practices are completely different. So, you take both cars again back to the factory after 6 months and do a health monitoring, you will see that they are very different. Both of us have driven it, let us say, for the same condition, for the same time, maybe for the same number of kilometers. Okay. So, now from that point of time, if somebody has to predict the life, he needs to know that what has this car been subjected to before that. Okay. So, that is what I mean when I say history of life cycle stresses. I may be a very aggressive driver, my friend may be driving only particularly mostly in third gear and fourth gear at optimally between 40 and 60 kilometers per hour. He may be slowing down well before bumpers and before speed bumps, but I do not do that. So, therefore, both of us have driven 10,000 kilometers in 6 months, but thereafter the health condition of both cars will be very, very different, right. Okay. So, based on these analysis, the life cycle can be proactively managed to minimize failures. So, what will I do? I am taking the car example again. The engineer in the factory will tell me that, sir, your car is not in good condition, you need to service it much more frequently than his, okay, or you need to get your brakes changed because your driving practices probably involves a lot of this frequent and strong braking. All right. So, at the end, what is physics of failure? Physics of failure is just good engineering. There is no rocket science. It is about understanding why the condition, the health condition of a product, what it can go through, and trying to predict based on physics, trying to predict how this product is going to degrade with usage and with time. Okay. All right. So, let us take the example of fatigue. So, we were discussing in the last class again what is fatigue. Material undergoes fatigue when it is repeatedly cycled under a certain load. Okay. In case of a solder joint, you may form a crack under this repetitive loading, which will propagate with time with more number of cycles and eventually lead to failure. Okay. So, this is a classic stress strain curve that you remember, right. We have studied this. So, the first part, what is stress? When you take any sample and put a load, then the load per unit area is known as stress. What is strain? Because of the loading, it will go deformation, either it will get compressed and therefore shrink in size, or it will expand, which will or grow in size. If you pull something, the length is going to increase. If you push something, it is going to decrease. And strain is this delta change, this incremental change in dimension over the original dimension. Okay. So, a material we call it elastic when it is in this first, when stress is proportional to strain, the constant of proportionality is known as Young's modulus. We have all learnt it in our high school physics. So, that is elastic. But if you keep on increasing the load and therefore increasing the stress, then what happens? We reach something known as the plastic region, right. In the plastic region, what happens is it is no longer proportional. In fact, with a little increase in stress, there is the increase in strain is much more. So, it is kind of yielding. Earlier it was resisting, now I give it a little more load and it is said, okay, I give up, I have yielded to the pressure. Okay. All right. So, this is known as the yield stress. Okay. And the rest of it, this one. So, now if you come to this point and then start withdrawing the stress, withdrawing the load and bring it down, it is not going to come back to the original position. It is going to come back with some residual strain, right. So, this is how it goes. Same thing, if you now apply compressive load, it is going to go down till here, this will be in the elastic region, but again then what happens is there will be this plastic deformation, and again as you bring it down, this is how it is going to happen, it is going to be. It may or may not come back to this exact point. I mean, these two have to be exactly equal, but I am trying to illustrate this one, right. So, when you apply a certain cyclical load, what happens? You take a stress specimen, this is how the stress is going up and down, this is how the strain is also going up and down, and let us say I do this repeatedly and I go to the plastic region. What do I see? At the beginning, this maximum stress and maximum strain, or for a given strain, for example, if the strain is held constant, at the beginning this is how it was, right. But later on what is happening is, here I started, I went like this, I came down. In the next cycle, as I increase the number of cycles, you can see for the given strain the stress goes up, and also for a given stress the strain goes up. So, this is fatigue, right. Earlier I could withstand a certain load with a certain amount of strain, but now, or I would bend, I would undergo a certain strain at a much higher load, but if you do it repeatedly, I am going to lose my strength and slowly I am going to yield much earlier. Okay. So, this is what happens. As you can see, the hysteresis curve grows up, grows bigger. This goes up, this goes down. Okay. So, fatigue in solder joints, if you look at it, again the same thing, you can look at it as high cycle fatigue, which operates in the elastic region. Sorry, there is a slight mistake on this slide. I am sorry for that. It can undergo something which is known as high cycle fatigue. So, high cycle fatigue operates in the elastic region where the stress is below the yield stress. Okay. But here the number of cycles is much more frequent, and that leads to what is called a high high cycle fatigue. Low cycle fatigue on the other hand is when von Mises stress is greater than yield stress. So, in this condition actually the failure is dominated by something called the failure is dominated by the stress, and in plastic deformation or low cycle fatigue it is dominated by strain. All right. So, let us look at this one. This picture we had seen before. Now, if you look at the strain on the solder, what will it be? It is going to be L over H if the solder height is H and L is the distance, in this case the distance of the solder joint that is farthest away from what is called the neutral plane. Then what is its deformation going to be? So, it is going to be L alpha delta T for the PCB and it is going to be L alpha silicon delta T for the chip. Okay. So, therefore, what is the net deformation? The board is going to deform more and the silicon is going to deform less. So, therefore, the net strain, which is the deformation divided by H, is going to be L alpha 1 minus alpha 2 or delta alpha minus times delta T. Clear? So, this is the shear strain at the edge solder balls. The ones that are in the inner planes that are closer to the neutral plane, that will be less because this L is going to be lesser for those, right. Okay. So, now if I look at fatigue in solder joints, this is the neutral condition, all right, and I am just starting from this point, this stress strain curve. In the next one, I go to the plastic region. So, this is my point and this is the condition where the PCB definitely has expanded more. Next, as the temperature goes down or comes to a state, original state, which is probably under the room temperature, this is what it is, it comes back again, but it does not come back to the original condition because it has undergone plastic deformation. You cool it down, it goes to this point and then it comes back. It may or may not come back to this point, by the way, but this is just a schematic representation. All right. Again, I must acknowledge Professor Abhijit Dasgupta, who presented a Gyan course earlier this year in 2018, and what I am showing are from his lecture notes, where he very nicely depicted this. I mean, it is known to all of us, but I think this was very nicely put. Okay. Again, repeatedly you will see on the slides, I am acknowledging two pretty well known stalwarts in this field, Professor Abhijit Dasgupta from University of Maryland and Professor Chris Bailey from University of Greenwich. Okay. They are both very well known in the field of electronic packaging. So, if you look at the solder joint fatigue in more details, high cycle fatigue is more vibration induced, you see here. Low cycle fatigue is more due to thermal expansion mismatch, and if you look at this one, what we were talking about before was kind of a global mismatch, right. So, this solder joint, we were seeing it as a single body undergoing deformation because of unequal expansion, right. So, this was the original condition, this is the on heating, this is what it is. But on the other hand, in reality, if you look even within the solder joint or the solder ball, if these are the four corners, you see the four corners are going to undergo stresses differently, correct. So, we need to understand these. This will see more strain, this will see more strain, these two not so much, 2 and 3 not so much, 1 and 4 much more, right. So, thermal cycling results or causes large slow cycles of inelastic creep strains generated by thermal expansion mismatch and resulting in low cycle fatigue. But the vibration, on the other hand, these are much rapid cycles of smaller amplitude because of flexure. If you have clamped on the two sides and you are vibrating, then what happens? It is undergo this flapping motion, flexural rigidity is kind of challenged and it results in high cycle fatigue. All right. Now, one may say that actually what happens is high cycle fatigue and low cycle fatigue. In actual solder joint, it may be a combination of both. So, fatigue life models. So, if it's high cycle fatigue is function of stress as we talked about, and Basquin model is something very well known. So, we have understood why this happens, okay. That understanding is there. Then what happens is you can now do a lot of analysis. Once you know, once you have characterized a material, you can do a lot of analysis using all these mathematical and computational tools that we have in our at our disposal today, and come up with an equation like this. NF is the number of cycles to failure, and that is given by this kind of equation, where SVM is the change in von Mises stress during loading, and A and B are material constraints, okay, material constants, sorry. Low cycle fatigue, which is probably more dominant in solder joints due to temperature cycling, that is a function of plastic strain, okay. And what you see here is, again, it is the gamma is the plastic strain, and the dependence, as you can see, C1 a constant times gamma to the power another constant, or 1 over another constant, okay. So, this is how it is. So, the second one is known as Coffin-Manson model, and after the two people who came up with this formulation, and we see a lot of variations of Coffin-Manson model today, all right. So, these are some examples, interconnect lifetime models under different conditions. Thermal cycling we already talked about. So, you can see these are kind of variations of Coffin-Manson model, except what is epsilon, that C2 is minus 1 over here. Under vibration, okay, it is more about high cycle fatigue, and there it is the stress that is important. So, the number of cycles to failure n is related to the stress in megapascals. Drop impact and voltage, if you apply, especially under components like transistors, solder, if you apply much higher voltage of a rise and drop repeatedly and makes it undergo through cycling, voltage cycling, then and this is actually, you can see this is sort of the two variable PEX model that we talked about in the last lecture. Here the two, what should I say, the two variables can be temperature, or can be relative humidity, and it can be the voltage, okay. All right. Now, what we will do is, it was more on solder joint fatigue. What we are going to talk about now is about a few other modes of failure. So, one of that is called popcorning. Now, what is popcorning? This is caused, number one, by, so popcorning is the failure mode. What is the mechanism? That is what we are going to discuss now. This is caused by, number one, moisture. For a change, you may say it is not temperature, it is moisture, but we will see temperature actually plays a role here. So, moisture is a killer, it is a cruel enemy of electronic products. It can really cause, really bad damage in electronic products. It can lead to corrosion, it can lead to a lot of other things. So, popcorning, and every material actually absorbs moisture, all right. We cannot do anything, especially plastic and all, they absorb more moisture, ceramics absorb less moisture, that is where hermetic sealing and etc. come into picture, but they are also more expensive. So, mostly for consumer electronics, these components will absorb moisture when subjected to certain atmospheric conditions, all right. So, moisture is a major threat. Now, let us say I have some components even at the manufacturing stage itself, and it is stored in normal atmosphere. So, it could absorb moisture. Now, let us I put this component on the circuit board and I do the reflow process. What will happen? Because of this fast rise in temperature, the absorbed moisture will vaporize. As it vaporizes, we know when something when water vaporizes, its density decreases, right. So, it will create immense pressure. So, there is a pressure build up, right. If you even take a simple P equals to rho RT type of state of equation, as rho goes up, everything else remaining constant, P has to go, the pressure has to go up, sorry, I am sorry, as it needs to expand and it cannot. So, there is a lot of, due to boiling, there is a lot of increase in pressure, I take back my state of equation argument. Okay. So, immense pressure build up within the package. So, what will that do? This moisture will try to come out. So, it will lead to cracks in the package. So, that because it wants to burst open and escape, and this bursting open is known as the popcorning effect. So, therefore, as a result, for any electronic component or system, what happens is, depending on the materials, the maximum storage time under normal atmosphere is given by something called MSL, standing for moisture sensitivity level. Okay. So, what we will do now is, we will look at a small video. So, let us play this, the link of which is on the slide. We will play this and listen to an expert talking about popcorning in package on package configuration, POP.
Popcorning can occur like any other component due to moisture in the package. Also, warpage is not uncommon with this type of package. Now, if packages do popcorn, the end result can be open circuits and solder shorts on the top two levels. You need to consider both the proper storage of these components and also the profile being conducted during reflow soldering to eliminate this phenomena. If the top package lifts during the soldering operation, when both solder ball and solder paste are in the reflow condition, what can actually happen is separation can occur and some solder can be drawn from one ball to the other ball. This can result in solder shorts depending on the design of the package. Also, the components can float, so you can get the top package floating above the terminations on the bottom package. This again results in an open circuit. Package on package is a fairly new process to many companies, but by thorough investigation, by doing production trials, you should be able to eliminate any instance of popcorning.
Okay, so we looked at what is popcorning, and you can see what can happen, right? Suddenly it's like just the popcorns. If you have ever fried popcorns, either in your microwave or in your pressure cooker, you would see this cracking sound. That's exactly what happens here, because as the pressure as it vaporizes, it wants to escape. It cannot. It is pressurized. Okay, so therefore it wants to. Therefore, that internal pressure at some point becomes so high that the material cannot withstand it any further and leads to this popcorning effect. Okay. The next one is called tombstoning, and this happens again during solder reflow. When you are putting a package, a surface mount package, and you are reflowing it, you will see that this can happen. Why? Remember, how does reflow occur? Because you have put a little bit of solder, and then when you put it inside the oven, this solder melts just that much to form this contact between the component and the board, and then it solidifies. Now, when this contact happens, when the solder melts, that is where the wetting happens. We call it wetting, solder wetting. That is essential for component attach, and then it has to solidify. Clear? Now, let us say one pad. Now, this is a. Now, what happens when the component is sitting on molten solder, how it behaves, how the wetting happens, how much the solder expands along the surface of the component, that all is driven by surface tension. So, now let us say if because of whatever reason, certain defects, one pad completes its wetting process before the other. Okay. So, therefore, one side solidifies earlier than the other is still in process. So, the wet pad therefore pulls up the other pin that is still in the process of wetting, and this results in the component, instead of being straight on the board, it kind of detaches at one end and lifts up, and in worst case it can become vertical, just like a tombstone. You know tombstone, where people are buried and you have this stone on top with their names written, some epitaph written. So, it almost like that, like it looks like that, the component is just standing up like a tombstone on the circuit board, where it is supposed to be horizontally aligned and attached on the board. Okay. So, you can see a picture over here. Now, again let us look at a couple of videos which will make it probably more visual and more appreciative. Let us look at this one. You see here the actual picture where a component, these are two solder pads and these are the two interconnects. Okay. This is, so ideally there should be wetted joint over here, a wetted joint over here, but what happens? There is unequal weighting, and you see along with time one side, the left side is getting wetted, the right side not so much, and you see this detachment, right, it has lifted up. And now this one started to wet, but by that time the detachment had already happened and the final configuration is a defective package. Okay. All right. So, let us look further. This one is actually another interesting video where somebody is trying to demonstrate the effect. So, this is kind of a manual operation and let us see what happens. You see a bunch of these solder pads where the user is actually manually putting some solder, dispensing some solder, and then he is going to put some components. The solder dispensation is still going on. And next what he will do, what you will see is he is going to take some components, small components with two interconnections and place them on each of these pairs. One. So, this is how he is now placing the components. Next he is going to heat up, so that the solder on both sides do melt and wets the joints. See what happens here. So, here it is not a reflow oven. What the user is doing, he or she is doing is, he has taken a kind of, I think, a hair dryer or some kind of a hand blower, heat gun, okay. And you see the way it is, they are all aligning, but this one, the fourth one suddenly lifted off, right. The one that he removed, that was an example of tombstoning. Okay. So, that kind of gives us a visual appreciation of what this tombstoning effect is all about. Okay. All right. So, let us look at some other failure modes. Again, acknowledgements to Professor Abhijit Dasgupta. So, at the component level, you see these kinds of defects or failure modes: capacitor micro cracking, dendritic growth, electromigration. We have not talked about them in details, but what happens is, if you have some of the atoms of one component does migrate into the other and leading to what is called the dendritic growth. Very, very essential, very, very common failure mode in batteries, lithium ion batteries. The cathode and anode can go through the, with time can actually go through the separator membrane and lead to internal shorting. Electromigration, wire bond corrosion, very, very essential. You see the wire bonds have corroded over here, probably due to moisture, due to some other chemicals or gases, corrosive environment. Die delamination, at certain point it has delaminated from the substrate, possible, right. Solder joint delamination is possible. Another thing, let us look into the next one. In PWBs, printed wiring boards, dendritic growth we talked about, plated through hole barrel cracking. Okay, that barrel, there may be a crack plated through. Remember that we, in the through hole, we did an inside plating, either electroplating or electrolytic plating or electroless plating. That can crack, that can be the plated through hole, that barrel can crack. Okay. Then trace fracture, pad cratering, there is a solder pad and inside actually there is a crater, there is a void, right. It can even be a void, it can be a foreign substance, clear. The other one again due to CTE mismatch is warpage. Okay, something that can warp so much that at one end the solder joints at one end may just separate out, because let us take this example of this wire board. Okay. So, if I may have the camera from the top, if I take this wire board for example, and this is, you can see this connector at both sides and I am holding it. Now, I heat it up. Okay. If I heat it up, then what happens is the silicon is going to expand to a certain level, the motherboard much more. So, now this, because this is held at the two ends, what will happen? In order to expand, it has to warp. It is no longer a straight line like this, but it will be a bent like. Okay. And this warpage, therefore, what will happen is from the end the connections may kind of open up. All right. So, this is important. Warpage is another big issue. Now, since I am showing this, let me also show you something very interesting. Say this is a ball grid array on an organic substrate or a package and on an FR4 motherboard. So, both are organic, the substrate is organic material, the motherboard is also an organic material. Okay. So, both this is an organic material, this is an organic material, similar CTE. Now, this is a ball grid array attached, BGA attached between the motherboard and the package as well as between the silicon and the substrate. Now, if you look carefully from the side, I do not know how much, probably yeah, you can see the outer, if you look along the edge, you can see the series of solder balls, right, at least the outer, the last row of the array. Other end also you should be able to see, but again this end was more clear, right. However, I do not see that outer joint over here. Why? Because we go back to our first level packaging, we talked about underfill epoxy. Silicon and FR4, because of the CTE mismatch, we use this underfill epoxy material, right, which results in reduction of the temperature induced stresses, clear. But why did we not have that between the package and motherboard? Because their CTEs are almost similar. So, why use it? Okay. So, there is no need to use, because both the package and the motherboard expand equally, but that is not the case between the silicon and the substrate or the package. All right. So, that is something very important, and that also since we are talking about solder joint fatigue etc., let us also talk about, or let us remember the concept of underfill epoxy, which is dispensed in order to minimize the effect. Okay. All right. So, in summary, this is a summary slide. Reliability, this is so we are wrapping up our whole discussion on reliability after 4 lectures. It is a critical component in the design of electronic systems. Okay. If you do not consider reliability, then you are doing a grave mistake, because it is not just performance today, but it is performance over the entire lifetime. You do not want somebody to say that, you know, this product X from this brand Y fails very early. It may be very good when you buy it, but you tell me after 3 months how it is performing. Okay. So, after 3 months you should be able to go and say that, you know, it is as good as it was on the first day. Then after 3 years also, depending on the product, you should be able to go and say, oh, it is still as good as it was. All right. Reliability prediction, that is important, that is part of reliability engineering. So, we can do it through accelerated degradation tests and statistical treatment, or we can do it as physics of failure analysis and modeling. Okay. The second one is more based on scientific rationale. The first one also, I will not say it is absolutely unscientific, because just the determination of what are the accelerated degradation conditions does require understanding of the primary mechanism, the root cause for failure mode, and determining what those conditions should be. But thereafter, it is no longer about scientific modeling, but it is more about collecting field data or experimental data in the lab and using that data to predict what should be the conditions under normal operating or what should be the degradation under normal operating conditions. Okay. So, that brings us to the end of this lecture as well as the entire discussion on reliability of electronics packages. Okay. So, what we will do is in the next lecture, when we come back, we will start on a new topic. All right. So, thank you very much, and we are going to come back again in the next lecture. Bye.